Well, hello, this is John Perham here, and I'm going to present my solutions to last week's test in MATH1131 algebra. So before we start with the solutions, I want to say a little bit about complex variables and the computer algebra system Mathematica, which I used to do everything, basically. One of the curious things about Mathematica, or it's not curious, is it treats all symbols to which a numerical value has not been assigned as complex. So, as an example of this, we want to look at the real part of x plus iy, and if we execute that, it will tell us that that's equal to the real part of x minus the imaginary part of y, which is correct, but not very useful. So, being aware of this, to do the same calculation but ensuring that symbols are treated as real variables or real numbers, then there's this function complex expand, and if we apply that, then we get x, which is what we'd like to get. So that's one of the foibles of Mathematica. These problems don't arise, of course, if we've got numbers instead of symbols. Now let's do a little bit about the arithmetic of complex numbers, because many of these test problems are about that. So let's start off with a complex number, which is z equals minus 1 minus root 3i. So the first thing we want to do is to calculate its real and imaginary parts, and we can do that with the functions re of z, which produces the real part, and the imaginary part. And you can see I've given those names of z. So the modulus of a complex number is computed as the square root of the sum of the squares of the real and imaginary parts. So we can compute it for this particular case here, and the answer is 2. And we can see that's correct. It's minus 1 squared is 1, minus root 3 squared is 3, 1 plus 3 is 4, square root equals 2. The argument, now this is kind of tricky, this one. We can write a complex number in this polar form involving its modulus times the exponential of I times its argument. And because of de Moivre's theorem, this is equal to the modulus times the cos of the argument and plus I times the sine. And argz is the unique angle theta in the principal domain, which is defined to be minus pi, less than theta, less than or equal to plus pi. And in this particular case, cos theta and sine theta will be equal to the real part divided by mod z and the imaginary part. So they're the values of those. How do we calculate those? Well, the principal domain of the arcsine function is minus pi over 2 to plus pi over 2. So we first compute an angle theta prime or theta 1, which is the arcsine of the second part here, which is minus pi over 3. And if the first value, cos theta, is non-negative, then theta prime is the correct value of argz. But if it's not, if cos theta is negative, the arg of z, or argz, will be pi minus theta prime if theta prime is positive, and minus pi minus theta prime if theta prime is negative. Should be. And we can put all this logic together to say that argz is if the first member, the cos theta, is positive, then the arg is theta 1, and if that's not the case, if theta 1 is positive, then it's pi minus theta 1, otherwise it's minus pi minus theta 1. So if we do that, we'll get minus 2 pi over 3, and that's fair enough. That's an angle in the third quadrant. So Mathematica, in fact, has a built-in function for doing this, which we're not going to use because I'm trying to use Mathematica to imitate somebody actually solving the problems by hand. Another way of doing the same thing is Mathematica has an arctan function, or it has two actually. One which has two arguments, the real, which are the real part and the imaginary part in this case, and that produces this result. Note that this is not the same as the arctan of the imaginary part divided by the real part, which gives pi over 3. Now this is very popular with students, but it's wrong, so don't use it. You've got to use your get the whole story using something like this. But once I've made this tool, of course, I can repeat it. We can think of these fragments here as reusable, customizable tools. Okay, so let's get on with the problems, and we'll start with the green problem set. So the first problem is to find the complex square roots of this complex number by solving this equation. Well, how do we solve that? Well, you may have seen my YouTube videos about this problem. If you haven't, you should have a look, but anyway, we'll do it. So we establish x plus iy as the complex variable z, and the left-hand side of this equation, see it there, is z squared, and we want to assume that x and y are real, so we get this, and the right-hand side is just this complex number here, so we'll establish that. Well, one equation for x and y can be found by subtracting the real parts of both sides. So we can do that here, and that'll give us an equation which looks like this. Now another real equation can be found by subtracting the moduli of the left and right hand sides. So the modulus of the left hand side is computed using this, and we're going to simplify it, and we're going to assume that x and y are reals. And then we subtract off the modulus of the right hand side, which is calculated using that. So this will give us another equation, and you can see that it's x squared plus y squared minus 61 equals 0. I always write equations in the form something equals 0. Well, we can see that if we add these two equations, then we'll get rid of the y. So we'll get a single equation for x by adding them. So let's do that. So we add the equations, and that's the result. So 2x squared minus 50 is 0. That's a very simple quadratic equation which we can solve using this. Mathematica knows how to solve quadratic equations, but we could have written that. So it finds two solutions, minus 5 and plus 5. Now we're going to find y. Well, we can't really use these two anymore. What I'm going to do is to take the imaginary part of the left hand of this equation equal to this. So so we subtract the imaginary parts and treating x and y as real variables, and we'll get that. Now you can see that this is 2xy plus 60 equals 0. So we can see immediately that the signs of x and y must be opposite. So we solve that equation for y. It's quite simple. And then we substitute in the values we've found for x, and these are the two solutions to the problem, namely minus 5 plus 6i and 5 minus 6i. So that's the solution to problem 1. let's go on to problem 2 now. So we're going to define two complex numbers, z equals 1 plus I and w equals 1 minus I root 3. So let's establish those. And we're going to find the modulus and argument of the complex number p, whose value is z to the 6th divided by w to the 5th. So let's do that. So we'll do the first part first, find the modulus. So let's open that up. And we can calculate the real and imaginary parts using our tool from above. And then we use the tool for computing the modulus. So it's the square root of the sum of the squares of the real and imaginary parts, which in this case is root 2. And now we do the same thing for w. So we compute its real part, 1, and its imaginary part using this, minus the square root of 3. And we can calculate the modulus of w, which is this. Well, now we can compute the modulus of p, because it's just the modulus of z to the power 6 divided by the modulus of w to the power 5th. So let's calculate that, and the answer is 1/4. So now we go on to find the argument. So we open this bit up, and to find the argument we copied all this stuff from above, and we want to calculate the values of the cosine of theta and the sine of theta, and we do that using this. And so theta 1 is the, we take the arc sine, and that's pi over 4, and if this cos theta is positive, which it is in this case, then this is arc z. So we apply our logic anyway. So if the cosine is positive, then it's equal to theta 1, and if the cosine, if the cosine is non-negative, and if the cosine is negative, then if theta 1 is positive, then it's pi minus theta 1, otherwise it's minus pi minus theta 1. So calculate that, and it's pi over 4, which is correct. Now we have to do the same thing with the argument of w, so we do a bit of cutting and pasting, and theta 1 is then the arc sine of this value here, which is minus pi over 3, and as before, here's the argument of w, and it of course is minus pi over 3. Well, to calculate the argument of p, it's 6 times the argument of z minus 5 times the argument of w. So we calculate that, and that comes to 19 pi over 6. Now, this is not in the principal range, and the way we get it into the principal range is to keep subtracting or adding, if this was negative, amounts 2 pi off until we get an angle in the principal range. Well, we can do that by subtracting 2 pi off and 4 pi off and see what we get. And we can see that the first, when we subtract off 2 pi, we get 7 pi over 6, which is not in the principal range. And if we subtract off 2 more pi's, then it's minus 5 pi over 6. So that's and that is in the principal range. So that is the argument of p, minus 5 pi over 6. Okay, so we'll clear that. That means that we deassign any numerical values to z and w. Problem 3 is to find the complex roots of this equation, p of z equals z to the 6th plus 3 to the 6th, and then when we've done that, to factorize p of z into real linear and real irreducible quadratic factors. So let's do that. So we write we write this as an equation. Z to the 6 is minus 3 to the 6, and minus 3 to the 6 is 3 to the 6 times e to the I pi, and then we can add 2n pi I to those values, and we'll still have the same complex number. So to find the solution of this, we now take the 6th root of this equation, so that will give us z equals 3, which is the 6th root of 3 to the 6, and then we divide these, so it's e to the 2n plus 1 pi I over 6. And for any integer value of n, that's their solution to the original equation. However, since a sextic equation has exactly 6 roots, we can evaluate the roots using this. So we take this this quantity here, which for any n is a solution, and we allow n to run from, say, minus 3 to 3 in steps of 1. So we do those, and we can see that we have to look to see if they're in the, well, they don't repeat themselves, and we can see that this is in the principal range, as is this, as is this. This one here is also, and is the complex conjugate of this guy. This one is in the principal range and is the conjugate of this guy, and this one here is also in the principal range and is the conjugate of this one. And we see that the 7th value repeats the first value. So we've found 6 roots, and we don't need to find any more. So anyway, if we look at these, we can see none of these roots are real. So, but if we multiply z minus, for example, this guy here, times z minus this guy here, the 5th one, then these two are conjugates, so that will be real. And the same thing will be true with the 1st and the 6th root, and then finally the 3rd and the 4th. So if we do that and put all those together, then we will get this thing here. And you can see that the first one's okay, z squared plus 9. This one is 9 plus a complex number, but it's the sum of a complex number and its conjugate, so that result is real, as is this one here. So this would be 6 times, or minus 6 times the cosine of 5 pi on 6. Mathematica has a function called x to trig, which converts these into real functions. And there it is. That's the solution. These are the, so that z to the 6 plus 30 plus 3 to the 6 is the product of this times this times this, and these are the real quadratic factors. Okay, so I think we'll stop there. That's the solution to the green problems. Now we're back, so we'll go on to the beige problems, or cream-coloured ones. So let's start with the first one. So we're given two complex numbers, z equals 3 minus 4i, which we can, and w is 1 plus I. And we're asked to calculate three things. The arg of minus 5w, 1 plus 2i times the conjugate of w, and then z minus 3i divided by w. So let's do those. So we define a complex number p equal to minus 5w, which is this guy here, and we want to calculate its real and imaginary parts. So we do that, and now we find its modulus as the sum of the squares of its real and imaginary parts. And now we find the argument of that. So we calculate the cosine and sines, and then we take the arc sine of the second member, which is minus pi over 4, and then we see that the first member is also negative, so the answer should be minus 3 pi over 4. So let's do that, and it indeed is. So that's the answer, that's the argument of minus 5w is minus 3 pi over 4. Well, Mathematica has a function called the conjugate function, so it operates on the complex number w, so we just multiply that by the conjugate, and the answer is 3 plus I. We could have done that the hard way, but it's only... And now, to calculate this guy, the quotient of two complex numbers, we know that we can express that as a complex number by multiplying the numerator by the conjugate of w and the denominator by the conjugate of w, because w times its conjugate is a real number, and by essentially multiplying and dividing by the same complex number, we're not changing anything. So let's calculate the numerator. So the numerator is z minus 3i times the conjugate of w, and the denominator is w times its conjugate, and the value of this complex number can be found by dividing the numerator by the denominator to give minus 2 minus 5i, and then we must remember to clear all the variables, deassign them. Problem 2, we're given this complex number z, 1 minus I, and we're asked to find the polar and Cartesian, i.e. a plus ib form of z to the power 10. So let's solve that. To find the polar form, we need to find the modulus and argument. So there's we start by finding the real parts and the imaginary parts, part of z, and then the modulus is the sum of the square root of the sum of the squares of the real and imaginary parts, which is the square root of 2. And then to find the argument of z, then we calculate the values of cosine and sine theta using that. And now we need to we use our algorithm. So we first of all take the arc sine of the second member, which is minus pi over 4, and we can see that the first member is also negative, so we'll apply a rule, and that should be minus 3 pi over 4, which indeed it is. So to calculate the argument of z to the power 10, we just multiply the argument of z by 10, which is minus 15 pi over 2, and which is of course not in the principal domain, it's negative. So what we do is we add 2 pi, 4 pi, 6 pi, and so on to this until we get a number which is in the principal domain, and we can do that by this arrangement here, computing the argument plus 2n pi for those values there, and we can see that these ones here are not in the principal domain. This one is, and this one isn't either. So the argument of z to the power 10 is e to the I, or is pi over 2. So the complex number expressed in polar form is root 2 to the power 10, which is 32, e to the I pi over 2. And the Cartesian form, well, e to the I pi over 2 is just I, so the Cartesian form is just 0 plus, maybe we should put that in, 0 plus 32i. So that's the solution to that problem. Now we go on to problem 3, and we're asked to use this identity that the cosine of theta is half the sum of e to the I theta plus its conjugate e to the minus I theta, to express cos to the fifth theta in terms of cosine of theta, 2 theta, and so on. So let's do that. Well, we do that simply by taking the fifth power of both sides and of this identity here. So the fifth power of a half is 1 over 32, and this will be this to the power 5. So we need to remember our expression for powers of x plus y as multinomials. So let's do that. So we take, we should remember this, but Mathematica does it. We expand that as a multinomial in x and y, and here it is here. And now all we have to do to customize that for our problem is to replace x by e to the I theta and y by e to the minus I theta in this identity here. And there we go there. And if we look at all that, we can see that that this term plus this term is the sum of a complex number and its conjugate, and this is just the cosine of, or 10 times the cosine of theta divided by 16, which is 5/8 cos theta. Now we go to this one here. We see that this term and this one are conjugates, so this will be just 5/16 times the cosine of 3 theta, and then this one here will be just 1/16 times the cosine of 5 theta. Or we could write it, if we wanted to be neat, to write that as 1/16 into 10 cos theta plus 5 cos 3 theta plus cos 5 theta. Anyway, so that's the solution of those problems.